welcome to session 7. Today's topic really is about Gram-Schmidt process. This is a process by which you take a matrix, square invertible matrix to begin with, and make it what we call orthogonal. So we have to understand what an orthogonal matrix is. We know what orthogonal vectors are, so we'll extend that to a matrix. And in order to understand that, we have to take one more step back and kind of revisit bases and also extend that to components of a vector. So let's get started. So the first part would be bases and components. As we saw last week, the basis of a vector space is the minimal set of vectors that would span that space. Or a subspace, it's the same thing. The minimal set of vectors. Minimal would mean that these are linearly independent vectors. If you have a linearly dependent vector in the basis set, that extra vector is actually kind of superfluous because it can be created by using the rest of the vectors. So that wouldn't be a minimal set. We saw that R2 needs two linearly independent vectors to span all of R2. Similarly, Rn requires n basis vectors. You can, of course, put these basis vectors in a matrix, the columns of that matrix. If you're talking about Rn, then you will get an n by n matrix because there are n vectors and each vector has n components and elements. What's the rank of that matrix? Since we know that these are basis vectors, they're linearly independent, so there are n linearly independent columns. That would mean that the rank of that matrix is n. It's a full rank square matrix. It's a good matrix. Now the thing to understand is that any vector in Rn in this case would be a unique linear combination of the basis vectors. What does that mean? You take the basis vectors, you scale each one of them by some factor and take a linear combination, and that would give you the vector that you're trying to construct. And that linear combination is unique, which will mean that all the weighting factors are unique, and those weighting factors are what we will call the components of the vector in that basis. So let's put that down in black and white. We have a vector x, a member of Rn, n real components. That means that vector can be expressed as a linear combination of the vectors that we chose as the basis vectors and put as the columns of the matrix A. So Ai, n of them, that would be the basis vectors and also the columns of the matrix A. So take a linear combination, and linear combination means you need some weighting factors. We're going to call that xi bar A. That is just a fancy name for the scaling factor Si. Keep in mind that Si's are going to be unique, meaning there will not be two sets of n numbers Si that will give you the same vector using the same basis vectors. Now, we said that these Si's would be the components of the vector x in the basis Ai. That's exactly what this guy means. The components of the vector x in the basis A, basis matrix A, which contains all the AIs as columns. So the coefficients that specify the linear combination, namely xi bar A, are the components of the vector in that basis. I'm defining this symbol and telling you that those really are the components of the vector. So given a basis, you can find only one set of components. Now the problem of what happens to these components when you change the basis, that is a change of basis problem. Before getting there, let's look at a very good matrix that we use as the basis. That is the identity matrix. Let's understand why it is a very good matrix for the basis. First thing that might be confusing to some of you is that when I specify a vector, I already have the components. I haven't specified any kind of basis set or basis matrix or anything, but you already have the components. Where do I get them from? Those actually come from the identity matrix, using identity matrix and its columns as the basis matrix and the basis vectors respectively. And it's also called the coordinate basis because the columns of the identity matrix, as you know by now, point, if you were to think of vectors as things that point in different directions, point in the directions of the axes in n dimension. Let's take something that is tractable, just 2 dimension. So suppose I take a vector x with components 2 and 3. Of course, x is the same as ix because I multiplying anything will give you just that anything. So I is right here. Then by the column picture of matrix multiplication, you can see that this product here is telling me that it is 2 times the first column plus 3 times the second column. And what's the first column? That is a unit vector in the x direction, direction 1. We will call that q1. And this guy similarly is a vector along the y direction, which we call q2. So you can see that it's a linear combination of two vectors. And what are those vectors? The columns of the identity matrix. And this linear combination is unique, and identity matrix is a basis for R2. So these are 2 and 3 are components of the vector that you started with, which of course you saw the components 2 and 3 in the identity basis. In physics, you call Q1 I hat and Q2 j hat, and Q3 in z direction k hat I j k. Those vectors are very important for a physicist. In any case, you can write the vector as having components 2 and 3 standing in a column, and you can put I2 because it's a 2 by 2 identity matrix. You can put that if you want, but nobody does that. And that's where the components come from the identity basis or the coordinate basis. So it's a perfect basis. Why? Because the columns are unit vectors. You can see that the columns are 1, 0. What's the norm of that vector? 1 squared plus 0 squared, square rooted is just 1. And also the columns are orthogonal to each other, because what is q1 dot q2, which is 1 0 dot 0 1, that would be 1 times 0 plus 0 times 1, 0, and that is the dot product is 0. That means the columns are orthogonal to each other, orthogonal and normalized, meaning they're orthonormal. And that you can write compactly by saying that the dot product of the ith column with the jth column is 1 if I equal to j, that means diagonal elements are 1. 0 if I is not equal to j, that means off diagonal elements are 0. Now we can use this fact and put it in a slightly fancier, mathematically fancier language to say that the dimension of the space is the number of basis vectors that you know, but the number of basis vectors also is the number of ones along the diagonal of this identity basis. And what's that? That entity, the sum of the diagonal elements, is called the trace of a matrix. So trace of I would of course be the number of columns or number of rows, and that is the dimension of the space that that identity matrix will span. So orthonormal is a desirable property for many reasons. The question then is, given any odd matrix, say A, can you create an orthonormal version of it, which you might be able to use as a basis? Not a random basis, but a basis that is related to that particular matrix, but still orthonormal. That, it turns out, is very important in computer science for a variety of reasons, which we will revisit later in this session. That process of making an orthonormal version of a matrix, well, when it comes to a matrix, people don't call it orthonormal, they just call it orthogonal. Orthogonal matrix is a matrix in which you have columns that are orthogonal as well as columns that are normalized. So that is orthonormal columns. A matrix with orthonormal columns is called an orthogonal matrix. And that process is the Gram-Schmidt process, which actually forms the topic of the day. So if you put the orthonormal vectors in a matrix, you can call that the orthonormal basis for that vector space. And the matrix is called orthogonal. When I started this course, I wanted to be very specific and call that orthonormal matrix. It turns out that people usually don't call a matrix with orthonormal columns an orthonormal matrix. They will just call it an orthogonal matrix. But let me tell you what it really means. We are going to use the symbol Q for orthogonal matrices, and that's got n columns. It's an n by n matrix, n columns, and the columns are linearly independent, and also they are orthogonal to each other, and also each one has a norm of 1. So it's an orthonormal set of vectors standing side by side, enough of them so that it can span all of Rn. And again, the condition is that the dot product of the ith column with the jth column is 1 if I equal to j, meaning if you take the ith vector and take its dot product with itself, then you get 1, which means the square of the norm is 1, which means the norm is 1. But if you take the dot product of one column with any other column, you will get 0. That means all columns are orthogonal to each other. This implies that Q inverse is Q transpose. Can you see why? Let me tell you why. Let's consider the product Q transpose Q. What's Q transpose Q in terms of the row column picture of matrix multiplication? Each element in the product, let's consider the element ij in row I, column j. What would that be? That would be the product of the row I in the first matrix with the column j in the second matrix. What's the first matrix? That is Q transpose. What's the ith row in Q transpose? That is exactly Qi transpose. And what's the jth column in Q? That's exactly Qj. So what's the product? That is 1 when I equal to j. That means the diagonal elements of the product will be 1. And when I is not equal to j, off diagonal elements will all be 0. What's that matrix? That's the identity matrix. So we can see that Q transpose Q is I. Similarly, Q transpose also is I. The dot product is commutative. Qi transpose Qj is the same as Qj transpose Qi. And another thing is that you can just take the transpose of this whole matrix equation here. I transpose is I, and this transpose will turn out to be Q transpose Q, as you know, from the product rule of transposes. That guy also is I. So I can say the condition for a matrix to be orthogonal, which means it has orthonormal columns, is that Q transpose equal to Q transpose Q equal to I. And what does this mean? That means Q transpose is the inverse of Q. That's why when it is multiplied on the left or on the right, you get I. So that is the statement here. Once you have an orthogonal matrix, you know that finding the inverse is child's play. You just take the transpose of the matrix. Very simple. No complicated computations there. And it also specifies a test for the orthogonality. So if I give you a matrix and ask you, is this an orthogonal matrix? The thing to do is just take the transpose, multiply it with the original one, and see if you get I. The second fact is that an orthogonal matrix will preserve the norm of a vector that it is working on. Meaning if it is transforming a vector, the transformed version of that vector will have the same norm as the original vector. How does that happen? Let's look at the square of the norm. So square both sides. So Qx norm the whole square, of course, is the dot product of that vector with itself. That is Qx transpose Qx. Then you know that Qx transpose is x transpose Q transpose. And then you know that matrix multiplication is associative. So you can group these two things together and do that first. That gives you just I. That turns out to be x transpose x, which is the square of the norm of x. That means the norm of this guy is the same as the norm of that guy. This also means that orthonormal matrices have unit determinants with a sign plus or minus 1. Can you see why? It also comes from just this fact here, which is the same as saying this one. If two matrices are equal, of course, their determinants have to be equal. Then you know that determinant of an inverse is the reciprocal of the determinant. Determinant of a transpose is the same as the original determinant. So Q transpose determinant is Q determinant. Q inverse determinant is 1 over the determinant of Q. So 1 over determinant of Q is determinant of Q, which means, of course, 1 is equal to determinant of Q square, implying that determinant of Q is plus or minus 1. Of course, the more illustrious ones among you would have seen that from here by the fact that the transformation Q applying on X does not change its norm. As you remember, determinant is like the size of the transformation. Now let's think about subspaces. What's the basis for a subspace? That, of course, is the same definition as the one for the space. The minimal set of vectors that will span all the vectors in the subspace. I can actually invert that statement and say that if I take a bunch of linearly independent vectors and create its span, that span is a subspace. And the linearly independent vectors that I start from, that would be a basis for that subspace. I just wanted to highlight the fact that it goes both ways. As you know, if I take two linearly independent vectors in R3 and form their span, then that would be a 2D subspace, a plane of vectors in R3. And these two vectors will be the basis for that subspace. Of course, you can find other bases if you want to, but these two would be perfectly fine as basis for that subspace. The important thing to notice is that if the dimension of the subspace is 2, you need only 2 vectors to span it. If you take one more vector in that subspace, of course those 3 vectors also will span the subspace, but the third vector is kind of useless because it's already a linear combination of the other 2. You cannot call the set of 3 vectors, the 3 vectors that we are talking about here, as the basis, because basis will have to be a minimal set of vectors to span the subspace. So any other vector in the subspace is going to be a linear combination of these 2 vectors. Let's take an example. We are going to take the same vectors that we started from in the last example in 2 dimensions, but we're going to add one more component to it. So it was 2, 1 and 1, 1. The 2-dimensional vectors, I just added a z component, 1 and 0. So if I put these 2 vectors in a matrix as columns 1 and 2, I get that matrix. And suppose I construct a new vector x deliberately by taking 2 times a1 and 3 times a2. So it's a linear combination of the columns of A, and the matrix A is the basis matrix. This vector, if I use A as the basis matrix, will have components which will be the coefficients or the weighting factors for the columns of A, so 2 and 3. So the components of the vector x is actually 2 and 3 because there are only 2 basis vectors. I need only 2 weighting factors, so it's 2 and 3. This might be a bit confusing to you at this point because you know that the vector x is actually a 3-dimensional vector. It's a vector in R3. It's got 3 components. But if I look at it in terms of the components of the basis of the subspace, you have only 2 components. That is perfectly normal because you have only 2 basis vectors. So you just have to specify how much you want to scale the first basis vector and how much you want to scale the second basis vector when you're taking the linear combination to make x. And those numbers are exactly 2 and 3 because by construction, I have x equal to 2 times the first column plus 3 times the second column of A. So that's the statement here. X in the basis of A has only 2 components. This is interesting and important to keep in mind. Now, kind of similar to this, let's look at the change of basis. Change of basis is actually used everywhere in multiplayer games. When you shoot at something, you see a particular view from your perspective. And what is going to happen is that on the server side, this is going to be converted to some kind of global server coordinate system that would be a basis change. Then if somebody else, the guy being shot at maybe, looks at it, he's going to see it from his perspective. That is another change of basis. And a couple of extra steps in between to go from the basis of the server to the camera basis and the perspective, etc. And this is an important application. And this for this reason that GPUs essentially implement matrix multiplications, and it turned out that matrix multiplications were important in LLMs too, and then people started using graphics chips, NVIDIA chips, not for gaming but also for LLMs, and that's the reason why the stock price of NVIDIA went through the roof. Now the question really is, suppose I give you a vector and new basis vectors, how do you change the basis? So let's look at that kind of mathematically. So the vector that I'm going to give you, let's say that is specified in the identity basis, and the matrix, the new basis vectors that are arranged as columns of the matrix are also in the identity basis. That would be the easiest thing to do. In fact, that's the only thing we will consider now. So we have our original vector that I gave to you in identity basis. We have the basis vectors AI, which are the columns of the matrix A, also in identity basis. Now we know that a linear combination of those vectors should give me x. That's why those vectors are the basis vectors, and those coefficients of the linear combination will give me the components. So the question then becomes, what are these xi in the basis of A, given x and A as numbers, columns of numbers. But if you look at this product, what is it? That's a linear combination of the columns of A. So linear combination of the columns of A is of course A times x, whatever that vector is. The vector has components there, and those components are basically just the vector in the basis of A. So it's identical to Ax equal to B. So Ax equal to B is coming back to haunt us again. So the way to get x, of course, is to solve for this equation. Now we know something extra about A. A is a basis matrix. That means it's a full rank square matrix, so we can invert it. So in order to get x in the basis of A, you will just write Ax in the basis of A is the same as x, which is what I've written here. That just says that this guy here, multiply both sides by A inverse, just A inverse times the original vector. Very simple to do. In other words, finding the components in a new basis is identical to solving a system of linear equations. Interesting, isn't it? So that's the statement there. So let's take a couple of examples here. So the first vector that I'm going to take, my vector is 7, 5, 7 units to the right along the x direction and 5 units vertically along the y direction. And in the identity basis, in the normal coordinate basis, I of course have components 7 and 5 because it is 7 times q1 plus 5 times q2. So identity basis is the same as what I gave you. Then suppose I take a different set of basis vectors. It's just that I'm scaling the first identity basis vector by 3.5, the second one by 2.5. So just scaling it. And now if you look at it, you can see that x is 2 times a1 prime, which is 3.50. So you get 7. And 2 times a2 prime, which is 2.5 in the second component. So you get 5 in the second component. So x in a prime as my basis is actually just 2, 2. Suppose I take another set of vectors, this time not scaled versions of q1 and q2, but in some random directions. A1 double prime is 2, 1, 2 units to the right and 1 unit vertically. So the red vector, my blue A2 double prime is 1, 1. You have to find a linear combination of those two vectors to get x. And if you do that, if you draw lines there and then take a few scale versions of it, you will see that it is 2 times A1 double prime plus 3 times A2 double prime. In the basis matrix A double prime, the components are actually 2 and 3. Interesting. This is a kind of limited in terms of visualization, so I have a visualization that you can play with. There you go. So we start with 2, 1 and 1, 1 as we did in my slide. But this visualization will let you change your green vector, can try to find components for any green vector, and also change your basis vectors to anything. And then you can see what's going on here. You can also see that the components are given by A inverse, A being the matrix in which you have these two vectors, A1 and A2 standing side by side. Take the inverse of it, and that is what you have in black right here. And multiply the vector, the green vector, by that inverse, and then you get the components, which you can see, visualize here. So as long as these two vectors, A1 and A2, can span all of R2 in this case, you're fine. But if you were to put them on top of each other, so if the basis vectors are collinear, they're dependent on each other, they cannot span the R2 space. So x cannot be expressed as a linear combination of these two. And my visualization is such that even when you put x right on top of these two vectors, make it collinear with the red vector and the blue vector, it still doesn't compute it because there are an infinite ways in which you can express the linear combination. You know all these things, but play with it and might be useful. So let's just summarize this. In the identity basis, we start with the vector 7, 5, and the components are 7 and 5 because identity basis is just 1, 0 and 0, 1. And the linear combination that gives you that vector 7, 5 is 7 times q1 plus 5 times q2. In my first change of basis, I just scaled q1 and q2. Then that gave me 2 times a1 prime plus 2 times a2 prime. So the components of x in a1 prime as the basis matrix is 2 and 2. Then the components of the vector in a double prime as the basis matrix, we saw that it was 2 and 3. And for any other vector, any other components, you can play with the visualization. One more thing, just to tell you that the computation is actually fairly simple. You just invert the matrix, the basis matrix right here, and multiply the original vector by that inverse of the basis matrix. And if you go to basis 2, 1 and 1, 1, the inverse happens to be 1 minus 1 minus 1, 2 column wise. Then doing the multiplication, you get indeed 2 and 3 as you saw in the visualization. If you don't believe me, Just do the longhand multiplication and you will get it. Computing the components of a vector in the subspace is a bit more complicated. So let's go through that. It's similar in spirit to what we just did. So if you take the vectors that span the subspace and put them as the columns of a matrix A, what do you have? Let's say the dimension of the subspace is n. The containing space would be the number of components of each one of the basis vectors. Since it's a subspace, that containing space will have a higher dimension, so it's m. So m is greater than n. So if you put these vectors as columns of A, you have m rows and n columns. M is greater than n, so it's a tall matrix. What we wanted to do was to take the inverse of A, multiply on both sides to get the components of X in the basis matrix A, the basis set which are columns of A. But you cannot do that because A is not a square matrix, so it doesn't have an inverse. So that's our dilemma. It's a tall matrix, it's not a square matrix. It doesn't have an inverse, but it is a full rank, full column rank matrix. Columns are linearly independent. It has a left inverse, and we do know that left inverse times the matrix, when the left inverse is multiplying on the left really, is I. So we can say that A times the vector expressed in the basis of A is X, the original vector, and the vector in the basis A is just left inverse times the original vector. That is just multiplying both sides by the left inverse. Left inverse times A becomes I. Left inverse times X is what you see here. So we know the formula for the left inverse. That comes from the fact that A transpose A is a small matrix, square matrix, and full rank because it's got n columns and n rows, and n is the number of linearly independent vectors in A. And you know that A transpose A has the same rank as A, so it's got a rank of n, and everything is hunky-dory. So A transpose A inverse times A transpose A is I, and what you see in green is the left inverse. So all you have to do is to do the long multiplication or get a computer to do it, and the inversion, then you will get the components. So let's do the computation here. I have a two-dimensional subspace in R3. So my M is 3, my N is 2. So 3 by 2 matrix here as a basis matrix. And we started with this. This, we already know the components because we constructed it. It is, was it 2 and 3 or 3 and 2? To compute the components of X in A basis, in other words, to compute the numbers that will be here. Remember, there will be only 2 of them because there are only 2 vectors here. All you have to do is to do that computation for left inverse. That becomes a 2 by 3 matrix, 2 by 3 matrix, and then multiply with the original vector here, left inverse multiplying the original vector. And that multiplication, after you do everything, it's going to be 2, 3, which is what we started with. So by construction, X was 2 times A1 plus 3 times A2, and we get it back. So this is a true by construction. This was the necessary background review that we needed before we went into orthogonality of matrices. In the next video, we will review the orthogonality of vectors first, and then how we extend that to matrices, or what it means to say a matrix is orthogonal, and that will lead to projections.